Let's talk briefly about units. You should already know that the SI unit for moment is the Newton meter, capital N, small m. But other units are possible. And you will find, for example, engineers often use pound-feet. So you can multiply any force unit by any distance unit and it's a moment. And you have to use a bit of common sense dealing with calculations involving those units. I'm not going to say any more about them. What I will mention though is this, that a Newton meter is actually an ambiguous unit. It can mean two different things. It's used both for moment and also for work. Now I hope you've met the idea of work or work done already. Let's briefly talk about it. Here's a force, there's a point, let's draw the line of action, let's give you the distance from the point to the line of action. There's no problem working out the moment. It's force times that distance, 20 newtons times 3 meters is 60 newton meters. No surprises. But here's another situation. Let's apply a 20 newton force to an object, and maybe that's the only force on the object. It will cause the object to accelerate. Suppose it accelerates over a distance of 3 meters while the force is applied. To calculate the work done by the force, which means the amount of energy transferred to the object, you probably know that the work done is given by force times distance. Well, it's 20 newtons times 3 meters. It's 60 newton meters. It looks the same as the top equation, but they mean totally different things. This 60 newton meters at the top means the turning effect, the moment or torque. This 60 newton meters means the amount of energy transferred. It would be the amount of kinetic energy that the object has acquired in this example. So Newton meters is a unit with two different meanings. Usually if you see it, it will be pretty obvious if we're talking about torque or talking about work. And usually work done or energy is given in joules. So instead of writing 60 newton meters, it would be more usual to write joules. But be aware, the Newton meter has two different meanings. Let's move on to the main part of the lesson. We'll start with a problem solving exercise for you. Here's a rod bar. Let's suppose its length d is 2 meters. Let's call the top point P, and let's apply force to the bottom of 30 newtons. Line of action of the force is there. Let's put the angle in so you know what the direction of the force relative to the rod is. 50 degrees. The exercise for you is very simple. Find the moment of the force about point P. Pause and have a go. Well, I hope you've tried it. The key method is to find the distance, a perpendicular distance from point P to the line of action. Let's draw it in. I've called it L, and it's perpendicular to the line of action. Now it's worth knowing that this distance L, the perpendicular distance from the point where we're taking moments about to the line of action, has got some names. It can be called the lever arm, or sometimes it's called the moment arm. So if you ever see those phrases, lever arm or moment arm, it's simply referring to this perpendicular distance. And to work out the moment of the force about P, we're going to multiply F, 30 newtons, by this length. So the problem is, how do we work out this length L? Well, if you look, we have a right angle triangle. The sine of angle 50 is the opposite side, which is L, divided by the hypotenuse, which is D. Let's write that down. Sine 50 is L over D, opposite over hypotenuse. So to get L, we have to rearrange it, and that will give L is D sine 50. Now it's easy to find the moment. The moment is the force times the lever arm. It will be force times, well, L is D sine 50. Stick the values in, and it comes to 46 newton meters clockwise. Now, I hope that makes sense. take a look at that. It's an important calculation. Let's talk about this formula. The moment is FD sine theta. We've just used it basically, but let's go over what's going on. Let's suppose we want to find the moment of force F about some point P. Let's draw force, let's draw point P down here. How do we do it? Well, let's suppose Q is a point somewhere on the force's line of action. So we draw the line of action. I need a point Q. It could be anywhere. It could be down the bottom here, it could be the tip of the arrow, in the middle of the arrow, at the tail, up here. Point Q could be anywhere. Let's mark a point Q up here. And let's suppose in the question we are given, so we know the distance PQ. So we know the distance from the point about which we are taking moments to some point on the line of action. We know it's distance D. Let's mark it. We know this distance D. Let's suppose we also are told, so we know the angle between the line of action and PQ. So we know the angle between this line and the line of action. Let's mark it in, theta. So we know three things: the force magnitude, this distance from the point where we're taking moments about to some point on the line of action. We know the angle between that line PQ and the line of action. How do we work out FD sine theta? Well, if you want to pause, you could try deriving it for yourself. So pause and have a go. Well, the calculation, the derivation I should say, is very similar to the calculation we did on the previous slide. Let's draw in the perpendicular, the lever arm, the line joining P to the line of action, so it's at 90 degrees, the line of action. That's L. Of course, the moment is simply F times L. But we know that sine theta is L over D. Right angle triangle, sine theta is the opposite, L over the hypotenuse D. Sine theta is L over D, so L is D times sine theta. The moment is F times L, so we substitute for L and get that the moment is FD sine theta. That's the proof of the formula, if you like. Now, can we use the formula? Let's have a go. Oh, before we do, I'd like to mention this. It's a useful point. Suppose theta is 90 degrees. Then sine theta is sine 90. And you ought to know that sine 90 is 1. That means this formula would become FD sine of 90. That would be FD times 1. It would just be FD. So if the angle theta is 90 degrees, we get our basic formula. Moment is force times this. Let's just draw that. It means that if point P is here and point Q is up here, so that we get an angle of 90 degrees, if theta is 90 degrees, then it's a simple situation where FD sine theta would be FD times sine 90. And that would simply leave us with force times this distance, if theta is 90 degrees. Now, a very simple exercise for you. Can you apply the formula? I hope you can remember it. Moment is FD sine theta. To this problem, what is the moment of F about point P? Pause and try that one. Well, it's simply a case of putting the numbers in. Let me mark Q for you, a point on the line of action, Q. There's the formula. We know the force 40. We know the distance PQ is 2.5 meters, and the angle between PQ and the line of action is 55 degrees. So all we have to do is say 40 times 2.5 times sine 55. It comes to 82 Newton meters clockwise, roughly. Does it matter which angle we use? We could use this bigger angle here. Let me mark it in green. What happens? Well, how big is it? You ought to know that the angle marked in green is simply 180 minus 55, which is 125. If you don't already know, let me tell you, sine 55 is the same as sine 125. The sine of an angle is the same as the sine of 180 minus that angle. And in fact, if we did the calculation using sine 125, it would give exactly the same answer. So we could use either the big angle, the obtuse angle, or the smaller angle, the acute angle. It makes no difference to the calculation. Now, here's a slightly harder set of small exercises for you. Here's a side view of a block. It's 40 centimeters high, it's 30 centimeters across. I'm going to apply a force to the corner, as shown, 12 newtons, at 60 degrees to side BC, 60 degrees to the vertical. And I want you to do 4 calculations basically. Can you find the moments of the 12 Newton force? First, what's the moment about point A? What's the moment of the force about point B? What's the moment about point C? And lastly, what is the moment of the force about point D? 4 separate calculations.